The project I'll present here deals with UAVs, which are unmanned aerial vehicles, drones. This is a real-life project, and what's required from us here is to supply a drone robot with some basic scene understanding abilities that eventually will allow it to navigate itself through the environment. More specifically, we are talking about an agricultural drone that intends to operate in arid environment, a desert. In the end of the process, the drone should be able to autonomously navigate itself on a daily basis to and inside the fields, collect and process agronomic visual data, and to alert in cases of identified agronomic problems. Almost every real-life visual recognition mission demands multi-scale identification ability, as the same object can be seen from far away or to be nearby the camera. Yet in drones, this requirement comes to its extreme. The variable flying height creates a distance range that could be much larger than the amplitude of distances that is normally encountered in other platforms, such as for example in autonomous cars. Moreover, the angle of the shots taken is dynamic and changes all the time. This heavily reflects with changes in the arrangement of the objects in the scene, as also with the parts of the target objects that are being seen or hidden, and even with their relative dimensions. Overcoming all this is one of the challenges involved in building a visual recognition model aimed for drones. This project was defined to be, at the first stage, a semantic segmentation task. Now, all convolutional models for semantic segmentation are operated in kind of a tricky situation. On the one hand, every convolutional model that aims to learn high-level representations have to contain pooling layers, but on the other hand, semantic segmentation architecture specifically must also project this spatially compressed representation back to original space, as they belong to the class of pixel-to-pixel models. Why this is a problem? Well, the pooling layers causes the model to lose information, but in the same time we need some of this lost information to reconstruct the final pixel level prediction. Dealing with this issue stands in the focus of the architectures for semantic segmentation. Many of these architectures are in essence pretty similar to each other and differ mostly in the bag of tricks they suggest to retrieve some of this lost information. Okay, so all these implementation details are of course important, but we're not the main problem I needed to deal with here. And the main problem was a big one, as I didn't have any relevant annotations for training my model. As I already mentioned, the target environment is very arid, a desert. And as far as I know, there is not even one publicly available drone-related training dataset that is relevant for this kind of a landscape. The few closest publicly available drone datasets I found were not close at all. For example, the UAV ID 2020 dataset that been created recently. This dataset is important and helpful, and its creator done a great job. Yet, in the context of my own goals here, the drone images of the UAV ID 2020 dataset were taken over extremely different landscape with different views and on a very different climate. Most of its images were taken in urban industrial cities, and all this together put it far, far away from my own target environment. The situation of lacking relevant image annotations is not rare at all, and many people encounter with it when facing real-life projects. Suppose, for example, that you are in a pre-seed stage of your own startup that involves visual recognition. If you cannot find publicly available relevant annotations that fit your own unique needs, you're in a big problem, because it becomes very hard to come up even with some minimal results to be able to show something to the potential investors. So you find yourself stuck in this frustrating loop, no proof of concept, no money, no money, no proof of concept. And the question is, what can be done in this unfortunate situation? Is transfer learning the answer? Well, no. Even when using transfer learning, and even if we consider the lowest possible threshold, the number of annotations that are still required for training reasonable size model are many dozens of images. And even that might be a serious burden, as manual segmentations of images is a tedious work. All this is true also when using other equivalent methods, such as self-supervised learning or any other method of pre-training. All these methods are extremely important, but will not give us a solution to the specific situation we are dealing with here. So, what is left to be done? Well, in some cases, one might decide to be satisfied with annotating rectangular bounding boxes, which is much more feasible than full manual segmentation, and this is certainly a serious option to consider. I, however, went here to another direction and came with my own different idea, and this idea started with a theoretical speculation. And it goes like this. Suppose that we have two very different target operation environments. For example, some industrial cities somewhere in East Asia, as appear on the left, and a rural area at the desert half a world away, as appear on the right. Now, suppose that for each of these two environments, we have in our hands a good, ready-to-go model for semantic segmentation of houses, roads, cars, trees, and low vegetation on images taken from drones, where both models are built on the exact same architecture template and only differ in their weights and biases values. My fundamental speculation here is that in this situation, if we would have looked at the function space of this specific neural network template, we would find that the two models are very close to each other on the function space axis. I emphasize that it is very crude, very simplified and informal qualitative statement, and due to the nature of the medium we'll keep it that way, without getting into more accurate quantitative definitions. But why do I claim that this speculation is true at all? Well, I claim that it is true because that even if the two environments are very different, walls are still walls and corners are still corners, and even if the colors, the design, and the exact fine-tuned shapes all could be very different, many of the inner principles that differs a building from roads or cars are still shared between the two environments. In most environments, roads and trees will probably don't have doors and windows, right? No matter if we are talking about a skyscraper neighborhood in New York or some humble village. I refer to it as inner level features. The on-surface details might be very different, but much of the essence is shared. Now, with this in mind, let's consider a practical situation. Suppose that we have enough training data to reach a good model for environment A, the one on the left, but for some reason, unfortunately, we managed to arrange only very few annotations for environment B, which is on the right. Just for the sake of the discussion, let's assume that we have in our hand only 5 annotations for environment B. So it is clear that with such a tiny training dataset, it is not possible for us to reach directly to a model that will perform well on environment B. However, if the speculation I represented earlier are true, the implication is that somewhere very close to the location of the model of environment A on the function space hides also a good model for environment B. As the model for environment A is accessible for us, this means that we will need only relatively very few number of additional update steps to move from the known model A to the unknown model B, if we would know which direction to go. But here's a question. If the two models are so close to each other on the function space as I claim, why is transfer learning will not be enough for us here for moving from A to B? Well, there are two problems with that. Catastrophic forgetting and memorization problem. What is happening is that in the moment we have in our hands a good model for environment A, and we try to go in a transfer learning way and continue from that point with the training process only with the 5 annotations of environment B, we now will be dealing with a completely new and inherently different loss manifold. If we could have taken a multidimensional glance at the average loss manifold of these 5 training samples of environment B, we would probably see some kind of a huge array of memorization tunnels that would be densely spread over the entire function space. The number of annotations for environment B is so small that it becomes very easy to memorize them. In this situation, many of the trained weights and biases that encapsulate information of environment A will be overrun, and the model will quickly converge to an overfitting solution. We also need to remember here that the loss manifold is a tough neighborhood. When we send the neural network to wander around there, we actually throw it to a jungle of gradients, where the strongest wins. And when you trained your model only with a scarce amount of samples, the strongest gradients would almost always be those who are leading to a memorization minima. In the bottom line, all this means that transfer learning is not an option for us here. So what is left to be done? My idea is that unlike in the process of transfer learning, after we're reaching a good model for environment A, we will keep training the model on the dataset of this environment, but now, in addition to that, we will also start to inject into the training process the very few annotations we do have for environment B. If the injections are done correctly and in a very precise and careful manner, The evolving model that started as pure environment A model will expand its scope and will cover also, to some extent, environment B context, and it will do that without losing its already acquired information regarding environment A. I'm looking at this method as a kind of an expand learning. We do not transfer the land representation, but just use it as a good starting point for a completely new process. What we do here is to expand the land representation a bit more, so they will cover also the patterns of another environment that is might be very different in its own surface features, but share most of its inner level attributes. Surprisingly enough, it's worked for me. In practice, I didn't even use the 5 annotations that we mentioned for the sake of the discussion. I used here only 2 annotations that I manually created. And this resulted with, of course, far from being perfect, but surprisingly reasonable results. This is the first annotation, aimed to represent a low altitude flight. And this is the second annotation for somewhat higher altitude. Okay, so first, let's take a look at the model at the point right after the training process have reached a reasonable performance on environment A, but before start injecting the 2 available annotations of environment B. In each column here, we can see a sample from the test set of the UAV ID 2020 dataset. The middle image is the ground truth, and the lower image is the prediction of the model. Same here. At this point, the performance of the model on the test images of environment A, the UAV ID 2020 dataset, are more or less reasonable. As a side note, I'll just mention that I had to apply here much heavier augmentations than generally implemented in similar tasks. This included very aggressive random zoom-outs, and this reflects with some loss of performance as the model is now expected to handle the same original objects but on the entire distance range from 100% to 20% of their original size. And this is not a trivial requirement. You can see an example for that on the left column. Anyhow, that's not really important right now. What we are more interested to see at this point is how this model will perform on images taken from drones flying over environment B. Well, let's take a look. And the answer is that it performs extremely bad. The exact category colors here are less important right now. The main point is that the model have a very hard time to even differentiate between the houses and their arid background. You can clearly see that most of the houses and the background are painted with the same grayish color, meaning that the model classifies them as they belong to the same category. This is of course not surprising, as at this point the model haven't even seen one sample from this very different arid environment. So now we continue the training, but as planned, we are starting to inject also the only 2 annotations I manually prepared for images taken from drones flying over environment B. After we train a bit the model in this way, we stop and check again the performance of the updated model. At this point, the model still performs reasonably on environment A, but now let's take a look how it performs on environment B. The class categories colors marks are gray for houses, light green for low vegetation, dark green for trees, black for roads, and transparent for background. In the following slides, focus for now only on the upper left image that combines the original image with the prediction of the model, and later you can rewind and look also of the other presentations. As you can see, we are now at a completely different game. The houses area is clearly separated from the background. From this distance plus angle, the model cannot separate the individual houses from each other, as many of them currently cover only few pixels. But the groups of houses are separated from the surrounding reasonably well. As the drone camera moves to focus with closer parts of the village, the model starts to show its ability to segment individual houses. Here we can see that the model even succeeds to some extent to identify a dirt road as a road. It also segments nicely the trees avenue on the right. However, it has some trouble deciding whether the vines at the fields at the left are considered trees or low vegetation, which is kind of reasonable confusion, as vines are actually really somewhere in the middle between those 2 categories. When I thought about this idea, my greatest concern was that while implementing my method, the model will just quickly memorize the two annotations of environment B, while keeping its generalization abilities of environment A. So I prepared in advance a large bag of tricks to try and prevent this from happening. Surprisingly enough, it wasn't necessary at all. There was not any apparent tendency for memorization. This probably implies that the gradient to this expansion minimum was very strong, which makes sense, as this corresponds well with the speculation about its proximity to model A location on the function space. Now a word of caution. Two annotations are by no means enough to represent the variability of views and details of an entire environment, even a small one. Even though the results were much better than expected, when using this expand learning principles, it would probably be advised to choose more annotations, so they will cover as much as possible of the environment variability under the obvious limitations of the method. Another important comment about the limitations of the method is that the model could not learn patterns that were not present at all at the base environment, meaning the environment of stage A of the process, in this case the UAVID 2020 dataset. Take for example this image that was taken from a drone flying over some area of the target environment. Many of the cliffy parts, or the large, more or less rectangular rocks, the model segmented them as houses. And when I tried to enter this image marked entirely as background to the training process in order to reduce this problem, the model indeed stopped marking those rocky cliffs as houses, but also lost some of its ability to identify real houses correctly. Meaning that we have here a situation of limited length blanket that we can pull here and there between sensitivity and specificity. Now, we know that neural networks could be trained to differentiate between very delicate differences, such as for example between different breeds of cats. But the thing is that nothing of this kind was presented at the base environment we trained on. Remember, the method described here could only expand existing patterns, it cannot invent completely new ones. Now, in the broader context, why do I find all this interesting? Well, there is the practical consideration, of course, as there are situations when this can be very useful. However, also from a more theoretical perspective, although the process of transferring a learned representation to different missions is extremely important, when you overrun the previous acquired knowledge in order to learn the new information, it seems kind of missing the point. Imagine a kid trying to operate a wood saw for the first time. The kid will probably use for this unfamiliar task the previous skills that have been acquired in using a simple kitchen knife to slice bread. But imagine that when the kid is learning to use the wood saw, he will forget how to use a kitchen knife. Not very efficient way of learning new things, right? So any technique or a method that will find a way to use previous information to acquire more information, to expand the knowledge and not replace it, seems as a step in the right direction. Okay, so that's that on this topic. Thank you and goodbye.